Hi, my name is Derek, and today I'm giving you an overview of our recent work on revisiting experience replay in non-stationary environments. This is a joint work with Andrew Jacobsen and Professor Adam White at the University of Alberta. In this project, we consider an online TD control problem and their model-free batch RL setting in a non-stationary MDP. In other words, let's imagine a scenario where we have an RL agent that goes out into the world, interacts with the environment, collects some rewards, and stores its experience as transition tuples. It then saves the transitions into a sliding buffer, what we call an experience replay, usually in a first in, first out manner. And during each training step, the learning algorithm samples a batch of transitions and uses them to learn a value function in order to improve the agent's policy and its online performance. So this seems nice. We have some data, we have a learning algorithm. So far, this sounds just like any other regression problem. So where's the real issue? In fact, one of the imminent problems here arises from the underlying data generating process. In supervised learning, we often have one or several fixed data sets to train our model with. But in this setting, because an experience replay is running buffer, and transitions keeps getting appended and removed, the distribution of training data is therefore often changing over time, and our learning algorithm faces the challenge to adapt to the non-stationary data stored in the replay buffer. And this poses a challenge. The non-stationarity problem here is usually caused by a multitude of factors. It could be the result of a non-stationary environment. It is also possible affected by our choice of function approximation. And finally, the policy we use to collect the data may have an influence as well, such as the choice we have to make in the classic exploration-exploitation trade-off. And these are just something we have to consider when we design the training process that involves an experience replay. Now let's walk through a quick example of the blocking maze environment to help us build some intuition around how a non-stationary environment may impact the data distribution in an experience replay. The left plot shows what the environment is like in the beginning, where the agent needs to learn to travel through the path to the right of the grid barrier in order to reach the goal and collect some rewards. As expected, the agent will have the most success learning from the states sampled along this trajectory. However, things flip around at the beginning of the second stage, where the barrier blocks the previous path and now leaves open a gap to the left instead. Now, all of a sudden, in order to collect the reward, the agent needs to learn more from this new path in order to reach the goal again. In order to do that, it needs to sample from a very different data distribution, as we could probably tell this time along the new trajectory. And some may argue that this makes experience replay ill-fitted for a problem like this. Nonetheless, this caused a particular bizarre problem for an experience replay because it could well contain data from both distributions during a certain period of time steps. I need to find ways to help our agents choose the right data to learn from. So in order to combat this problem, we need to develop an adaptive sampling strategy. For this exact reason, we propose a non-uniform sampling method that can be used in combination with other existing methods, such as the prioritized experience replay. Our method has a built-in tendency to sample more recent state transitions in order to be more adaptive. We define n to be the number of times a state action pair is sampled, and our sampling probabilities at each training step follow an exponential distribution over this heuristic. By sampling more recent data, it helps the agent to make use of transitions that are close to being on policy. Overall, this makes the learning process more stable and also more robust to changes in the environment. In addition, when we design experience replay, we often choose an appropriate replay size based on the memory constraint and the complexity of the problem our agent is solving. However, the non-stationarity of the data in the buffer can also make a huge difference. Our method helps decouple this design choice from the non-stationarity of the underlying data generating process, which relationship is often overlooked in practical RL because it's rather counterintuitive to build this connection. And what's more, the degree of non-stationarity is also not exactly a measure that's easy to quantify or estimate. So it's actually nice that we can avoid this when designing an experience replay. And lastly, our method unifies and generalizes two very different sampling strategies, namely between sampling uniformly over all past experience available versus purely online. And this allows us to trade off between sample efficiency and adaptability. And it basically allows us to take the best of both worlds. It depends on situations. And to the right is a simplified example of how our method works. Please feel free to check out our paper if you're interested in more details. Now let's take a look at some of the results from the blocking maze experiments that we previously mentioned. Here we have an online agent as a strong baseline under this non-stationary environment. This is shown as the red learning curve. And we are comparing the online performance of the prioritized experience replay, aka PER, which is the go-to standard these days for an experience replay, and this recency biased variant, which is the method we propose. The learning curves of PER are shown in green to the left, and the learning curves for our method are shown in purple to the right. Our experiment contains 30 runs in total. Each run has 300 episodes, as shown on the x-axis. As previously pointed out, the environment changes from phase 1 to phase 2 at about the 150th episode, where as you can see, there's a sudden drop in performance in the middle of the agent's lifetime, and then followed by a rebound. On the y-axis, we have the average steps per episode as our metric. The less steps an agent takes, the better. In the left plot, we could see that as we move from using a small buffer to using a large buffer, as the color of the learning curves darkens, PER's ability to adapt to non-stationarity in the environment starts to degrade quite significantly. And in comparison, the chart to the right shows that the recency biased version does not really suffer the same problem nearly as much as vanilla PER does. Now here are some additional results from our sensitivity analysis from the same experiments. The x-axis shows the indices of the step size parameters we have searched through, and the y-axis shows the agent's average online performance. The higher, the better. Again, the agents in comparison here include the online agents as a baseline under the non-stationary setting, labeled in red, and 4 other agents using experience replay and their study here, including our method, recency-biased PER, which is colored in purple. It is quite clear to see that while with a tiny replay buffer, all experience replay agents are able to achieve superior sample efficiency than the online agent as expected, since using an experience replay allows them to reuse past experience and break the correlation in data. However, as replay capacity increases, the performance of agents using a replay starts to worsen, and to the point they could no longer adequately complete the task, as we observed from the blue, orange, green sensitive learning curves, sensitivity curves, except for our method in this case, which outperforms all the other methods in the tiny and media buffer setting and stays competitive with the online baseline in the more challenging larger buffer setting. In summary, we demonstrated through experiments that the non-stationary environment and distributional shift in the replay buffer is detrimental to the learning process of an RL agent, which is a crucial problem to solve if we want to deploy our agent into the real world eventually. And furthermore, the problem is becoming more pervasive as we observe an ongoing trend where larger experience replays are becoming more and more popular as modern large-scale problems are getting more and more complex for deep RL system to solve. And finally, recency bias sampling is just the first attempt to address this non-stationary data adaptation issue in highly non-stationary and high-dimensional environments where large replay is required. And we encourage researchers in our community to look into this problem and come up with better solutions. This is the end of the talk. Thank you all for listening.